Great, thanks, Kevin, for the introduction and the opportunity to be here. So today I'm going to be talking about some work I've been doing for a long time on autonomous robot learning for manipulation. Oh, let me get that. There we go. And so right off the bat, I just want to acknowledge all my collaborators. So my lab at Utah on the left, who I've been working with for the past 5 years and will be most of this talk, but also some collaborators, my PhD advisors and my postdoc team, because I'll be showing some older work to kind of set a broader stage. Okay, so as I said, I'm primarily interested in robot manipulation, and we focus mostly on autonomous manipulation. And we really would like robots to be assistants in our daily lives so that, for example, we can age at home longer independently, or have them be assistants at work sites to help us move heavy objects without injuring ourselves, or send these robots into hazardous environments where we don't want to send people. And kind of a key issue across all of these tasks is the ability for robots to fluently manipulate objects with which they have no previous experience. Sorry. So this is going to be the foundation of a lot of the work I talk about today. And a natural question that arises is, why can't we do that today? And you might think that robots simply don't have the dexterity or ability to perform manipulation at the level we want. This is a video of the Utah MIT robot hand. This hand is nearly as old as I am, and over 30 years ago could skillfully perform these manipulation tasks of changing this tube, which we're just now trying to do autonomously. So I think the hardware was not the limiting factor and hasn't been for a long time. Additionally, on the hardware side, you might think sensing isn't sufficient for the kinds of tasks we want robots to do. And while I totally advocate that we need more sensing, and particularly more tactile sensing and coverage on our robots, this example works here from my group, I think, show that we can use tactile and haptic sensing to do very skillful things like picking and placing this deformable water bottle without crushing it. And that the sensations and perception itself is not the limit, but actually what we're doing with that information. And so what is missing? To think about this, let's think about what classic approaches to robotic manipulation do. And so they typically require some sort of model of the object in terms of its 3D shape and inertial properties. Or they have some human providing teleoperation or some sort of task-specific demonstration or program. So much of the knowledge is being engineered into the system before acting. So as an alternative, what we'd like are representations of objects and the environment that the robot's operating in, that the robot can autonomously construct using their own sensors and actuators and validate, that they can efficiently learn, and they can leverage for efficient planning and control. And so, what we really like is if you see a scene like this, so this is like the coffee preparation station in my kitchen, we'd like a robot to look at this and see the kinds of things that we do too, right? That we can easily grasp these objects potentially at these handles that we're seeing here. That we can place these objects onto this large surface at these different locations. That we can potentially remove these lids or replace these lids onto these objects. And even be able to slide or pull these joints we're seeing here, or push these buttons. And the common representation that I've been using to reason about all of these kinds of inferences is the idea of affordances and affordance learning in robotics. Right, and so I'm going to assume most of you are familiar with the idea of affordances, but just the definition that we generally use in robotics is kind of a paraphrasing of Gibson's definition, which is that the latent action possibilities available to some agent in an environment. And so the agent is going to help define kind of what the capabilities are, but importantly, the environment, we're going to assume that's fixed in our case, that we have the same robot learning over time. But the environments are going to change, and we want to have a large set of actions or skills that the robot can perform across different objects and And so to this end, kind of the standard model in robotics is this undirected graphical model of the idea of the action, the object, and the effect. And I'm going to leave this at a very cartoon level for this talk and use it to organize some different learning work we've done in terms of learning object representations, actions, and learning to predict effects. And so I'm going to start by talking about learning object representations. So here's an example image taken from a PR2 robot, and the robot would like to be able to manipulate objects in the scene. And we see that we have this plank of wood on top of a wooden table. And so there's a high color and texture overlap in terms of the visual information. Also, the tactile information is quite similar between the table and this object. And so this work was done 8 years ago now, right around the time that the Microsoft Kinect came out, which is a 3D depth camera. And so we can actually solve this problem of segmenting this object that the robot hasn't seen before quite easily using simple geometric information, just assuming there's a plane that's supporting the objects. However, this is actually a bit of an unfair trick to the robot because this is not one object, but two. And the point of this, while it's a pathological example, is that perception is inherently ambiguous. And we would like to not just make predictions that the robot has from a single observation, but instead have the robot autonomously interact with its environment to validate hypotheses it generates about its perceptual information, such that it has representations it can leverage for planning and control in terms of manipulating these objects. So that's what we're going to do. We're going to have the robot push these objects to find individual rigid bodies in the scene. The general kind of principle for this work is that we can hypothesize potential segmentations based on visual features in the scene by simply finding planes in the scene and saying where two objects might be. Then given this planar separation principle, the robot can plan a pushing operation based on that plane to try to validate or invalidate its hypothesis, right? So it's going to try to push here, this object on the right, this hypothesized object on the right, parallel to this plane, so that if it is separate from the purple object, it will move and the other one will not. And we can detect that and by reasoning about the 3D rigid body motion of the object. And so here's an example of the robot performing this task for this for these three objects. So you see in the top right, the hypothesis that there's a separating boundary between the medicine bottle and the mug. So the robot pushes and it separates this medicine bottle. It's now doing the analysis to verify that this object didn't move relative to the other two. It validates that and is now going to push the bowl to try to separate it from the mug, which it successfully does. But importantly, after the robot retracts its arm and validates that the bowl moved, it's actually going to perform one more push on the mug because it sees a reflection in the base of the mug. And it's not confident that it's actually not two objects. And so to finalize that, to confidently know it's found all the objects, the robot's going to perform one more push and see that the object does move as a single rigid body and can therefore be confident in its segmentation of the scene. Okay. So with this work, I've shown a way that robots can discover representations of novel objects through interaction with the environment, where we're going to explicitly validate hypotheses that the robot generates through autonomous action generation. And if we think about this from this affordance triple idea, then we're giving the robot a set of actions, pushing behaviors, and a set of effect measures, so rigid body motion, that it can use to validate these hypotheses and find objects. And while we've done this with actions, pushing and rigid body motion here, this general framework we've used in other contexts as well, including tactile perception of objects in terms of classification, 3D reconstruction of objects, both with touch and vision, and inertial property estimation. So mass, center of mass, moment of inertia, using tactile sensing as well. So some limitations about what I've shown here is that we're learning object-specific models. So they're not going to generalize in a way that allows us to quickly leverage this knowledge when we come across other new objects. but they do allow us, the robot, that is, to understand the objects it's interacted with previously. Additionally, we're making rigid body assumptions here. These aren't super strong, but things like pushing towels or rope wouldn't work well in this scenario. So now I've shown a way of creating object representations autonomously. I want to talk about a way of generating and learning action effects in an autonomous manner. And so I'm going to use the example of multi-fingered grasp learning, which is an area we've been working on a lot for the past 4 years. And we take a supervised learning approach where the robot's going to generate a large-scale data set of grasp attempts in simulation. We use simulation mainly so we can generate a large amount of data, but also so we can have ground truth automatic labeling of the data and not have to rely on some secondary system or a human to do it. The robot's going to learn a classifier to differentiate successful and failed grasp attempts, with the desire that this classifier is going to generalize to novel objects that are previously unseen to the robot. Furthermore, we're going to use this learned model in a novel way, in a form of a constrained optimization problem to perform grasp planning. And so I'll talk about a little bit about the details of this model now. So I said we're going to learn a classifier, and we will, but we're also going to learn a grasp prior, which is a sampler. So the simple model here is we're going to take just the positive examples, so the successful grasp attempts, and learn a mapping from the sensor input in terms of the RGBD image patch to the grasp configuration, which is the 6 degree of freedom wrist pose of the robot, as well as where the joints are of the fingers before the hand closes, so the pre-shape of the grasp. We can learn this as a mixture density network, where we're essentially learning the parameters of Gaussian mixture models conditioned on this visual input. So we could use this sampler, given a new image, to quickly generate many grasp hypotheses in the scene. However, these are they don't work too well if we just directly execute them, because they're only roughly encoding some of the constraints we know about grasping. And additionally, they can only learn from the positive grasp examples and not also learn from the negative grasp examples. And our data sets tend to be fairly imbalanced with more negative examples than positive. So to combat this, we also learn a classifier that takes in the grasp configuration theta and the image patch z and predicts the probability of success y. This classifier then can be used in conjunction with the prior to perform a map inference, so maxima a posteriori, to find the grasp configuration theta, which is most probable under the posterior probability over these two learned models. And the important thing here for us in learning these models as neural networks is mostly that they're differentiable and allow us to efficiently solve this optimization using modern quasi-Newton methods where we can add constraints on the problem. So for example, here are the kinematic joint limits of the hand, but we've also shown we can do things like obstacle avoidance as constraints in this planning problem. So we can engineer knowledge that we know is important to the robot and not have to learn that. Okay, so additionally with this probabilistic interpretation, we can actually perform active learning with these models. And I'm not gonna talk a ton about this, but the main thing I wanna show is that in using this active learning criteria to explore the possible grasp configurations, we can achieve higher success rates with lower amounts of data, while also achieving a higher diversity of grasps compared to a heuristic passive learning technique that we had used previously. So here are some examples of grasp generated by the model learned through active exploration. Additionally, through this and other works, we've shown the ability to generate a wide variety of grasp in terms of overhead and side grasp, as well as precision and power grasp. So the overhead and side are actually learned in a somewhat unsupervised manner and through this prior density learning. Whereas the precision and power grasp, we explicitly add as labels, showing that we can add symbolic information into this learning paradigm to provide more constraints on the grasp learning if it's desired by the application. So here's an example of the robot doing some grasp. I'm going to skip this for the sake of time, but it's just to show you that this really does work quickly on the real robot where it's presented with a novel object here and can quickly pick it up. So I've shown you now a way that we can learn to predict action effects on novel objects. So we've learned these skills on the physical system that generalize to previously unencountered objects. And here we're assuming we have some object segmentation that could be derived through these interactive procedures I showed before. We also have some planner that's telling us in a fairly structured way what the action we want to do is, here grasp and lift an object. And then we also need the ability to label the success or failure of this attempt in the simulator for training. So these are fairly strong assumptions still. In this case, I showed you how we could learn a classifier. We have shown other works in the context of pushing and slip detection, where we can instead learn a continuous cost to reward function. And additionally, this work is leveraging engineered low-level controllers and planners to help the learning be efficient, right? Compared to something like a model-free reinforcement learning method that would have to learn to reach and perform the grasping technique. We want the robot to really focus on learning the part we don't know how to do, which is represent the object from this partial view information in a way that it can leverage for planning. Additionally, we can incorporate model-based constraints jointly with this learned components so that we can give the knowledge we have or engineering kind of constraints that we might require for certain applications. So we don't require that the learning do everything. So finally, I'm going to quickly talk about some work we've done on learning actions. And to motivate that, I'm going to use this example of moving object collections. So if you think about having a pile of coins, say on your table that you want to put in your pocket, you don't need to explicitly reason about the number of quarters, nickels, and dimes in that group, but instead can reason about the objects as a collection. And we wanted to provide robots with this capability, as this is very different from typical paradigms we use in manipulation, where we typically want to know about all individual objects. So we're going to have a robot learn to push collections from some initial configuration to within a new square. And we can generalize the goals, and we're also would like that this robot can generalize in terms of the number of objects it sees, and potentially also the types of object it sees. So as with the grasp learning work, we're going to do a sim to real training paradigm where we're going to have the robot learn in simulation, but we're going to set that simulation up in a way that the behaviors the robot learns directly translate to the physical robot without any new learning. And we're going to use a two-phase training process where the robot first learns a state space representation of the environment, which we're going to call phi, and then uses this learned representation to learn image-based policies to perform the pushing actions in a reinforcement learning paradigm. And like I said, we're going to try to test on different types and numbers of objects. So without getting into too much of the details, the main contribution here is that we're using graph neural networks to be able to encode this variable number of objects. And we're going to learn what we can think of as a graph neural network autoencoder to go from the poses of the objects in the simulator to predict those same poses, both from the ground truth poses and from an image-based representation. We're again going to use a density output here, so we don't have to do any data association in providing the loss, and can train simply using a standard maximum likelihood loss. Once we've done this initial supervised learning of these latent spaces over a large collection of random pushing actions, we then use an asymmetric actor-critic approach where we give the reward function from the ground truth poses, but learn the policy directly from the images so that we can operate in the real world. And so here's an example of our work compared to an image-based autoencoder that doesn't have the same graph neural network structure in it. And we see that our approach can more quickly push these objects into the goal configuration without getting stuck that we see the autoencoder does. So additionally, like I said, the structure we've learned is able to generalize to different numbers of objects. So we can do, we trained the RL policy only on 10 objects, 10 cubes. We also tested it on 1 cube or 20 cubes and had nearly perfect success. We also tested on a pile of silverware and just a pile of crumpled up paper balls. So just objects we just kind of thought were interesting collections to work on, and saw the robot again, was successful nearly every time. So one area that it wasn't as successful for is, I think, maybe more interesting for the common sense kinds of results we're looking for, which is when we start with the objects spread out, a significantly harder task, we actually see that the robot has learned novel actions to group the objects into configurations that make it easier to push them towards the goal. So we're seeing here that this representation learning in terms of how to encode the objects as a collection is actually helping us improve the kinds of actions the robot is capable of learning. So I've shown you how robots can learn novel actions based on intuitive or autonomous exploration, where we're giving the only the object representation in terms of the state in the simulator, and an effect measure in terms of a simple reward function of success or failure. We can, this is the first work to enable pushing of object collections of unknown type and number in robotics. We've done similar work to this in terms of learning actions from tactile representations for in-hand manipulation tasks, as shown here, with very different kinds of models. And I would say that some limitations of this work currently is we're only encoding, we're kind of treating all objects the same and not actually learning anything about their geometry or appearance or semantic information, which is likely important for tasks that we care about robots achieving. So kind of the final question that comes up after showing you that we can learn these actions, objects, and effect representations is, can we do this jointly? And that's exactly what we're looking at currently through this, my team is looking at in this DARPA MCS project. So we're looking to learn unified multisensory object representations across multiple tasks, where we're going to learn novel classifiers to capture new effects that the robot discovers on its own, and use planning to generate novel policies in these paradigms. And we're going to continue to leverage simulators for this ground truth supervision and the use of expert planners for demonstrating great behavior. So here's just one final slide showing some results of that, where we have the robot learning to segment its scene jointly with learning to perform these pick and place actions. And we're looking to integrate this both with the exploration strategies that Ori talked about, learning from RoboCup, as well as through the symbolic planning that Alan talked about this morning. So with that, I can conclude my talk and open it for questions.